In this talk, I will tell you about one way towards the next level of capabilities of in artificial intelligence and machine learning. So let me tell you about the OpenAI universe. What we built is a platform for training the ability of machine learning systems to solve a truly wide variety of general tasks and for evaluating this ability. The goal of the universe is to make it possible to develop systems that can solve a wide variety of problems that are difficult, and a system that could solve them quickly. So the way universe works is that it provides programmatic access to a machine learning agent to any computer program or website that exists. So here is a random sampling of the environments that are currently integrated into universe. These happen to be computer games. Universe makes it likewise easy to integrate the web browser. And therefore, all kinds of tasks that humans do that appear in a web browser context, like filling a form and performing in effect knowledge work type tasks. Here is an example of real websites and a human demonstrator performing prescribed tasks on them, in this case booking of flights on different websites. Universe also makes it possible to integrate large, difficult games, which are shown here. So, for example, protein folding and large 3D games. We've recently made it easy to use GTA as well. So, why is this good? The reason it is good is because if we are to build an agent that has a general problem-solving ability, it needs to be exposed to a great variety of problems. And how are you going to get this variety of problems? And in short, there are two ways. One of the ways is that you just build it yourself. You design all the problems yourself. The second way is that you use an existing source of problems. And the motivation here is that human beings today, even though we live in a physical world, we spend a significant fraction of our lives in the digital world, in our computers. And so there exists this rich digital world that we live in. And the number of applications and tasks that we perform there is vast. And so that becomes a natural place in which we can train our agents to achieve a similar level of general intelligence and problem-solving skills. This is the aspiration of universe. This is what we hope to enable. The way it works is described roughly in this diagram. The environment is run as a process on some computer, and we created a plumbing that can capture the pixels from the environment and send them to the agents, and vice versa. The agent can send keyboard and mouse commands to the environment. So you can see that this, in principle, allows the agent to interact with any program if only it has the ability to do it, if only, and the problem becomes into one of how to train the agents to succeed in doing so. So let me say a few words about the current state of universe. So at this point we have 100 fully integrated environments, where by an integrated environment we mean one where we have all the details set up, including a reward function, which we handle by means of OCR on a score. We also have over 1,000 of integrated environments that do not have a reward. And we plan to integrate large, more intricate environments in the future. So what's the goal? So let me reiterate the goal of universe again. We create all these environments with the goal to train an agent that would have the world knowledge and the common sense and the problem-solving abilities, so that you can plug it in to any new environment, give it any task, and it will quickly figure out what the task is, what it needs to do, and then do it. This is something that humans do really well, but our machine learning algorithms do not. Right now, a machine learning algorithm lacks common sense, and it must be trained on only one task in order to achieve high performance on it. And we want to create the additional ability that humans have that machine learning algorithms currently do not. So, some technical details on how Universe works. So, a program is launched in a Docker container, which is a lightweight virtual machine. We use the VNC remote desktop protocol to communicate between the process that runs on Docker and the agent. And we can even send the pixels over the public internet. So in this figure, what the figure depicts is a set of 32 environments which are running on the cloud, and an agent which runs on 2 GPUs on our server. And what we observe is that it takes about 30 milliseconds for our actions to be sent to the agent, and about 100 milliseconds for the observations to be sent from the agent back, from the environment back to the agent. So this suggests that it's possible to configure and use Universe in a wide variety of configurations that can be really convenient. It makes it really easy to integrate new games into Universe, and we've just applied the reinforcement learning algorithm on the game Slither. Some of you may have played, where your goal is to grow a snake, and you do this by avoiding other snakes and eating them whenever they collide like here, for example. And we've also got rights to distribute environments and games from a significant number of publishers. So, as a result of doing this work, it will be possible to train agents to achieve general problem-solving ability. But then the question is, how are we actually going to do it? What would be the machine learning approach that will allow it? And in the second part of the talk, I want to highlight one particular research that was done at OpenAI, primarily by Rocky Duan, whose photograph is shown in this slide, on the work named RL squared, which is fast reinforcement learning via slow reinforcement learning. And the idea there is really simple. What we really want, we want to learn to solve problems as fast as humans do. So we can try to speculate about the mechanisms by which humans do it. And the short answer is, humans have already a lot of experience in solving lots of different problems. And because of this experience, they take this experience to the new problem. We can formalize it as follows. We have a distribution over tasks. We have a set of tasks that we believe that our agent should be good at. And we want our agent to be able at solving new tasks from the same distribution of tasks. This formalization doesn't quite capture everything that we want, because we want to be able to solve tasks that fall outside of our training distribution of tasks. But in this work, we only look at the simpler case, when the new task comes from the same distribution as the training tasks. So let's see how it looks like. Now here, I'm just pointing out some things that we can expect to learn from our training tasks. Let me get to the high level. The high level is this. Our learning algorithm is going to be a recurrent neural network. It will be learning inside of its activations. And let me just tell you the training criteria in 2 sentences. So it's worth focusing, it's worth paying attention to the next 2 sentences. Basically, what you want is the following. You want to take your recurrent neural network agent and place it in any one of the many training environments that you have. And then you want it to do as well as possible on a training environment without knowing what it is in advance. So, you have a recurrent neural network policy, so it has memory and state. And it's placed in a new environment, and it needs to figure out how to do well in this. So let's illustrate it with examples. So we have a recurrent neural network which sends actions, and it gets to receive both observations and rewards. So notice that the recurrent neural network sees the rewards as well as inputs. This is how it gets to understand what the environment is and act in effect like a fast learning algorithm. So during training we say, okay, here's an environment, do as well as possible on that. Here's a different environment, do as well as possible on that. This is actually not, even though this figure is shown as a static square, in reality it's a dynamic environment. And again, and so what will end up happening is that the weights of the recurrent neural network will learn a general policy that will not memorize how to solve every environment. Instead, it will be able to roughly have a strategy that it will look at some of the attributes of the environment. It may take actions to explore it, to understand what kind of environment it is in. It will do a really good system identification and then solve it. So some more figures of the same, and there is quite a bit of related work. There is work by DeepMind, a simultaneous publication with a similar title. There's been work by Andrichovich, meta-learning by gradient descent by gradient descent, Sontaro, one-shot learning memory augmented networks, La Rochelle, zero-shot learning with new task, Junger. There's been all of this work is an example of meta-learning, where we use a machine learning algorithm to learn something which learns at test time. And what we do falls into this as well. Let me show you the detailed formulation. So you run your recurrent neural network for several episodes in one environment, then you reset the hidden state and you run it for several episodes in the next environment. And you do policy gradients or any other slow reinforcement learning algorithm you want. We only have 2 minutes left, so I want to quickly jump into describing the results of how well it works. The short answer that it works pretty well, but there's still a long way to go. So we started by evaluating it on simple reinforcement learning tasks for which optimal algorithms exist. So specifically, the tasks that I'm talking about are multi-armed bandits tasks. For those who are not familiar with it, a multi-armed bandit task is a task where you have lots of different buttons, and different buttons give you different payoffs. And you want to get the largest payoff that you can, so you go and click on the different buttons. And at some point you need to decide if you already know what the best button is, or keep pressing on more. But it doesn't even matter. The point is it's a task, it's of academic interest, and people have studied it a lot. And we have been able to outperform some of the asymptotically optimal algorithms on small instances of the problem with a short time horizon. When the time horizon is relatively short, we've been able to beat the optimal algorithm by quite a bit. And it makes sense. The optimal algorithm optimizes performance in the long term, while we can perfectly tune performance in the short term with our meta-learning. The other kind of tasks we've considered are tabular MDPs, where you have a randomly generated MDP with a small number of steps. And these too have optimal algorithms. And we've been able to outperform the optimal algorithms as well whenever the horizon is short. So when the horizon is short, you can see that we are doing quite well. As the horizon gets longer, we eventually lose to the algorithm, to the optimal algorithm. And finally, we've applied this algorithm to maze navigation. We can interpret maze navigation as meta-learning, where you need to learn the maze. You go to a new maze you've never seen. If you can solve that, it means that you already have the ability to learn information about mazes. So let me show you some example. So you see a video here of the agent doing random stuff before it learns. And I'm going to show you what happens after it learns. It walks around and it looks for the target, and it keeps looking for the target, and it looks for it some more, and now it found it. And next time, it already knows where the target is, so it finds it much faster. So this is how success looks like. Success has not been uniform, because we've observed that sometimes the agent fails to learn to perform the task. Like here, it walks back and forth without remembering to make the turn into the appropriate place. And we've been able to get good performance on small mazes, and the policy has also generalized to large mazes. So, to conclude, the universe is in effect a task where if we solve it, we will develop an agent with general problem-solving abilities, and we presented preliminary research in this direction which showed interesting results, and it will get better in the future. And yeah, there are quite a few ways in which you can push it forward, but ultimately you can see these discussions in the publication. Thank you very much for your attention.